the Euler's method. Firstly, the rate curve represents the exact particular solution, which is obtained by solving the first order differential equation as shown, which will give me y equals to square root 2 over third x cubed plus 4x plus 1. However, an exact solution is not always possible to find, and this is why we use the Euler's method as a numerical approximation. To begin from the known initial condition, y bracket 0 equals 1 highlighted here in green, the differential equation gives the slope of the solution at this point through the function f bracket x comma y equals dy dx. And instead of following the exact curve, the Euler's method assumes that over a small interval, the curve behaves like its tangent line. And as shown here, the step size h equals 0.1. Also, h denotes as the step size. We can start from the initial point 0, and then we can move horizontally by 0.1 and calculate the new y value using the Euler's formula, which is shown here, yn plus 1 equals to yn plus h times function x bracket y. And this gives us our first approximate point. We then repeat the same process over and over again using the new approximate point to calculate a new slope and estimate the next point. And these points form the blue linear approximation in the graph. And as you can see, the blue approximation follows the exact solution closely at first, but gradually deviates from the rate curve. This happens because each new point is an approximation, so small errors accumulate with every step. And using a smaller step size like 0.1 would reduce this accumulated error and produce a more accurate approximation. So now I'm going to show you how to do it in the Excel file. So as you can see, to find my y value, I use the previous x value, and then I plus 0.1, which is my step size, times the dy dx, which is the previous x value square, plus 2 divided by the previous y value. And then after I find it, I just drag it down like this, and then you give me the other values as well in the column. So for dy dx, I also did something similar. So I use but this one is different. So I use the current x value square, then plus 2 divided by the current y value to find the dy dx at this new point. So this represents the dy dx at every point in the row. And then we can see that y bracket 1 equals to 2.403. So that's to 3dp. That's the Euler's method's approximate y bracket 1 value. So I can show you how I did the particular solution. So first we find the general solution, as you can see, and then after I find the arbitrary constant, I sub it in to find the particular solution, which is here, y equals to square root 2 third x cubed plus 4x plus 1. And after that, I sub in x equals 1 to find y bracket 1, which is y bracket 1 equals to 2.380. And next, I'll be explaining about absolute error and percentage error. So firstly, absolute error measures the numerical difference between the Euler's method approximated value and the exact solution's value. It tells us how far the approximated value is from the true value. Regardless of the overestimated or underestimated approximated value, it can also be seen as always positive as we are finding the absolute value. That's why this value right here is not negative, and we are finding only the magnitude. So for percentage error, which is 0.9% as shown, it means the Euler's approximation differs from the exact solution by less than 1%. And this indicates that the approximation is highly accurate for a step size of 0.1. And as you can see, this formula right here is the relative error, which compares the actual difference with the exact value given by the general solution. Thank you.